online session conducted by SAP for engineering students. The topic for today's session is Spread Spectrum Communication of Digital Communication. The session is conducted for 6th semester students of Electronics and Communication Engineering. The session will be handled by Mr. Nandan S., Assistant Professor, Department of Electronics and Communication Engineering, LBS Institute of Technology for Women, Trivandrum. He has more than 8 years of experience in academics. He completed his BTech from Kerala University and MTech in Telecommunication at National Institute of Technology, 𝐂𝐬𝐿. Previously, he worked with 𝐶burst Technologies, Trivandrum, 𝐒𝐫𝐨𝐝𝐿 College, Trivandrum, and LBS College of Engineering, Kasaragod. His research area of interest include wireless communication, 3G, 4G mobile communication, cognitive radio and MIMO OFDM systems for communication. He has also done funded projects in embedded systems and robotics for Center for Disabilities, Government of Kerala. He has more than 20 publications in international and national journals and conferences. He is also active in various international professional organizations. He is currently the chair of Student Activities Committee of IEEE Kerala section and secretary of Internet Society India Trivandrum chapter. On behalf of SAP, sir, I welcome you to the session. To the participants, the total duration of the session is 1 hour. The session comprises of 2 halves each. 20 minutes of lecturing and 10 minutes for Q&A. The students can ask their questions in the Q&A box. Sir, once again, welcome to the online class. You may please proceed with the session. Thank you.
Okay. Thank you so much. Thanks for the introduction. So, hi all. Today we will have a session, a brief discussion about spread spectrum communication system, which is basically the topic under the 6th module of digital communication of ASICS Electronics and Communication Engineering. All right, so we will try to give a brief concept or outline of what basically is spread spectrum communication and the fundamental concepts of that, and if time permits we will discuss the mathematical model of that, the mathematical analysis of some of the parameters of spread spectrum communication system. So let us formally start. So here is the outline of the program of this particular session. So we will be discussing spread spectrum communication fundamentals, the basic concepts. Then we will deal with some of the parameters. Then we will be discussing the different types of spread spectrum communication. One is direct sequence spread spectrum, and the second one is frequency hope spread spectrum. Then we will check, if time permits, we will discuss the model for analysis, some mathematical analysis of some of the parameter processing. Okay. Now let me quickly with some basic concepts, and I request, the students are requested to have some prerequisites of some of the digital modulation schemes that we normally use in digital communication systems. Normally we have some fundamental modulation techniques like Bpsk, 𝐻𝐵Psk and all. So I request students to have some prerequisites of this to well understand the concepts of spectrum. Okay. Anyway, you might have studied in a communication system 2 primary resources that we are using in a communication system is nothing but bandwidth as well as power. Okay, so these two are I should say specifically these two are the major concerns while we are designing a digital communication system. So these are the 2 primary communication resources. We always try to limit this bandwidth as minimum as possible, as well as we will try to limit the transmit power as minimum as possible. All right, so these two are some of the primary communication resources that we are normally concerned about. All right, now we use these 2 resources, communication resources, with utmost care, right? So we try to reduce this bandwidth as minimum as possible, as well as the transmission power. Any communication system you take, we will try to reduce the transmission power of the communication system as minimum as possible. So these two are the primary concerns normally in a digital communication system. But there are some situations where we sacrifice the efficient utilization of these two resources. We will have some adjustments in this. We will sacrifice either bandwidth or power in some design objectives to get some objectives. All right. So one such example is a secure communication system. Now, what is a secure communication system? A secure communication system means you want to transmit data securely, secretly through a communication channel. You don't want your data to be detected by an unintended user in the channel. You want to transmit the data with maximum security from the transmitter side to the receiver side. Where if security, for example, military applications, where security of the system, security of the transmitted signal is of utmost importance rather than the transmit power or the bandwidth. So there are some situations, as I told, there are some situations where we will sacrifice this efficient utilization of these two resources. And a very good example for that is a secure communication system. All right. So here in a secure communication system, my design objective is noise dropping. Right. I don't want anyone to listen to data what I am transmitting through the channel. I don't want anyone to listen to my data. I want to send it secretly, securely to the receiver end. That's my design objective basically in a secure communication system. There comes the significance of spread spectrum techniques. So there comes the significance of spread spectrum techniques. All right. So now let us discuss what are the different spectrum techniques. What is the fundamental concept of this spread spectrum communication system. All right. So my primary advantage is to have the ability to reject any kind of interference. Interference can be either intentional or unintentional. Intentional means purposefully a jammer will be sitting in the channel who is trying to take my detect. We call it as eavesdropping, right? So that is intentional, and in some cases it may be unintentional also. So anyway, whether it is unintentional, I don't want my data to be detected by an intermediate, a receiver, unintended authorized receiver. That's my primary objective, and that is a primary advantage of a secure communication system, or I should say a spread spectrum technique. So using a spread spectrum technique, we are basically getting some advantage of security of the system by compromising so-called previous resources, bandwidth, and some extent power. All right. So now let us define a spread spectrum system. Spread spectrum system is a means of transmission of data. Data has information, right? Data will carry information. So it is actually a method of transmission in which the data is spreaded over a wider range of frequencies. Right. Actual data will be a very narrow band signal. Normally we call it as a baseband signal, significant low frequency components. Right. So actual data will be a very narrow band signal. Now I will spread that narrow band signal to a wider band. I will spread that narrow band signal to a wider band. This is what we are doing in spread spectrum communication. We are spreading, from the name itself it is very clear. We are spreading spectrum. We are spreading the spectrum before transmitting the data. So before transmitting the data, we spread the spectrum of the data we will transmit. This is a fundamental spread spectrum. So spread spectrum, I can say it is a means of transmission, it's a method of transmission in which data is spread over a wider range of frequencies. Actual data is narrowband. Now I will spread it over a wider range of frequencies, than what is actually required. All right. Now, for a given transmit power, what I am doing in spread spectrum, I am spreading the spectrum. All right. So for a given transmit power, broader the spectrum means the signal power is less. The signal power is less. So for an unintended user, for an unauthorized user, the detection or the interception it seems to be difficult. Why? Because I am spreading the entire power over this wide range of frequencies. All right. So this is the fundamental idea behind a spread spectrum. So with some diagrams, you will come to know a little bit more clear about the fundamental concepts of a spread spectrum system. All right. Now the question is how you will spread the spectrum. How the spectrum is spreaded. The spectrum is spreaded by means of a code. I'm using a code. All right. I'm using a code, and this code completely independent of the data sequence. There is no relation between this data sequence and the code that we are using. Okay, so the question is how you will spread the data. All right, how you will spread the data? By means of a so-called pseudo noise code. What is pseudo noise code? You might have studied some pseudo noise sequences, right? We will discuss in this, in the upcoming modules, we will be discussing pseudo noise sequence, its properties and all. So pseudo noise sequence means it seems like noise, but it is not actually noise. It is following a particular pattern. It seems like noise, but it's not actually noise. So by using pseudo noise sequences, I will spread my data, and there is no relation between this code and actual data. All right, this is what I am doing. All right, so now you listen carefully. You can see here what I'm doing is I'm using a pseudo random code. I'm using a pseudo random code to spread the signal. This is the bandwidth or the spectrum, I should say. This is a spectrum of your actual signal. The figure shows this one. This one shows the spectrum of your actual signal, which is a narrow bandwidth. This is the bandwidth, right? Bandwidth is very less. Now what I am doing is using this pseudo random code, I will spread the signal, spread this bandwidth to a wider spectrum. This is what you are transmitting. So here the bandwidth is very high. And what I am doing at the receiver side, coming to the receiver side, I will despread using the same code that I am using at the receiver. Whatever code I am using at the transmitter, I will use the same code to get my signal back, data back from the spreaded signal. All right. I hope the concept is clear. So I have a narrow band signal, which is having a very less bandwidth. Now I will spread this bandwidth with the help of so-called a pseudo random code, and with the help of this pseudo noise code, I will spread the spectrum. All right. So the overall bandwidth seems to be very high, and the total power is now spreaded over this wider bandwidth region. So this is a spreading thing. And now I will use the same PN sequence code at the receiver to despread to get back your actual data. This is the concept. All right. Now I'm reiterating, in a spread spectrum system, the transmitted signal occupies a much larger bandwidth than required. All right. So I'm reiterating, in a spread spectrum system, the transmitted signal occupies a much larger bandwidth than what is actually required. All right. Now the question is, how do you widen the bandwidth of data signal? That is a question. All right. Normally the question will arise, how we can widen this bandwidth of the signal? I told you, right? How it is possible with the help of something called a code, a pseudo random code. Now let us see how we can spread the spectrum of your actual data signal with the help of this code. All right. So how will you do this widening? There comes block diagram of a spectrum system. So we are having a data encoder, right? We are having a data encoder which will encode the data, right? Some data you are coming which will take care of the source part and all. So some data which is coming from the source, which will be encoded by the data encoder. Now that encoded data is now given to a spread spectrum modulator, right? And what is happening? What we are taking at the input of this spread spectrum modulator? We have the data as well as the pseudo noise code generator. So we have a pseudo noise code generator. Output of this pseudo noise code generator is called the spreading code. Spreading code. Normally we call it as a spreading code, which is nothing but so-called the code signal. Normally we call it as a code signal. All right. We call it as a pseudo random code signal or a pseudo noise code signal. All right. Now I will use these two and I will spread this data with the help of this pseudo noise code and I will transmit to it through the channel. Right. So what is here? What you are getting here in this particular portion is nothing but this spread spectrum system. signal, sorry, spread spectrum signal. All right. So this data is having, the data here is having a very narrow bandwidth. After spreading here, coming to here in the channel side, the bandwidth of the overall signal increases, or I should say spreading will happen. So that signal which is passing through the channel, I call it as the spread spectrum signal. All right. Now, coming to the receiver side, I will use the same spread spectrum demodulator where, I will use the same code signal. Whatever code I am using at the transmitter, I will use the same code at the receiver to do the exactly reverse process of what I have done at the transmitter side. Okay, and once if you despread, that process is called despreading. Once if I despread the data, then I will decode it to get the actual data output. And please remember, I haven't mentioned anything about the channel noise here. Obviously, while passing through a channel, some sort of noise will be there. All right. So finally, after despreading, you will get your data back. I hope it is clear. Now, here goes a spread spectrum communication, the whole concept. What is this spreading actually? See, here I have mentioned spreading, right? A spread spectrum modulator. Here goes. This is simply a multiplier. See this? See the figure? You can see very well in the figure. We actually have, this is your input data, D of t or by B of t, whatever, right? Let it be, I represent it as D of t, which is the data signal, which has the information, which is a very narrow band signal, bandwidth is quite less. Now I am simply multiplying with the code signal C of t. C of t is my code signal. I am multiplying this C of t with my D of t. And that pure product or multiplication is nothing but the spreading thing. We call, spreading is actually simply taking the product of actual input signal with your code. So spreading is just product of taking the product of input data signal with the code. So output of this product is, this product modulator is nothing but a transmitted spread spectrum signal S of t. All right, which will be having a spreaded spectrum. You can see here the bandwidth is very less. Now here coming here, once if you multiply with a code, the bandwidth spread. If you multiply with a code, the bandwidth of the data signal will spread. Now, at the receiver, you are getting R of t, right? You are getting that spread spectrum signal at the receiver. Now what I am doing, I am multiplying this code signal. I am multiplying with the same code signal that I am using at the transmitter, right? To get back your Z of t, which is again despreaded version. Despreaded version is exactly ditto of what I have transmitted at the transmitter side. All right. So this is the general, the whole idea of a spread spectrum communication system. So we are simply taking the product. All right. Now, once if you closely observe this particular thing, then the spread spectrum fundamental concept will be very much clear. All right. So you please observe this. You please observe this. In the time domain, I have shown here the time domain approach. All right. So assume that this is my data. This is my data. So my data is say 1 here and 0 here. Okay. All right. So what I am having here is, this is my data. All right. This is my data. So my data is having, suppose they 1 and a 0, which is represented in the polar form. So 1 is represented as +1 and 0 is represented as -1, polar form, normal polar form, right? So 1 is represented as +a and 0 is represented as -a, right? So what is the time period of my data signal TB? This is one bit that I am transmitting, 1 bit of my information. What is the time period? TB is my time period. All right. So this is my data signal. Now what I am doing is I am having a code. Here is the code. See here, with inside the table you can see the code. My code is having here 001101 is my code here. All right. And see what is the length of this code? 1 2 3 4 5 6 7. 7 is the length. I'm having a code I'm having a code with seven chips, so-called chips. Right. I call it as a chip. Right. So my code length is actually 7. I represent with capital N. What is capital N here? 7. What is capital N? Capital N is the number of chips in one particular code. So I have here 001110 7. 7 is the length. So my capital N is 7. Now I will represent this code again in the polar form. So 0 is represented as -1. 1 is represented as 1. All right, and the very simple polar form. 0 represented as -1 and 1 represented as +1. Okay, so this is a polar form representation of my code sequence. Now, see, one bit of my data which is having TB duration is multiplied with this code. See, this is my code. See here 0, here 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, which is the code. Or I should say -1, -1, 1, 1, 1, -1, 1. This is the code. So this is a 7 length code. Right? This is having length 7. Capital N is equal to 7. All right. So one bit of my actual data is multiplied with this particular code, which is in the polar form. What you will get? 1 multiplied with. So see here, please observe the thing. What is the period time duration of this code? TC. I represent as TC. For data, it is TB. TB is the bit duration. TC is the chip duration. I call it as chip duration. C represents chip or code, maybe. Okay, so TC is the chip duration. This is the duration of. So as compared to your data, your code signal is having a lesser time period. All right, that is a whole concept. As compared to your data signal, which is having a time period of TB, my code signal now is having a duration time period of TC. TC is very small compared to TB. All right, and can you tell me what is TB? TB is equal to N times TC. Why? Because I am having N number of such chips, some sequences. So N times TC is TB. All right. So if I multiply these two, then what I am getting is -1 multiplied with 1. You'll be having here. See here, 1 multiplied with -1, -1 again, -1 multiplied with 1, -1. All right. So you are multiplying the data signal with this spreading code. You are multiplying this particular data signal with this spreading code. So 1 multiplied with 1, you can see here 1, 1, 1. So product of these two, product of first two will be this. So the third figure here, the third product signal M of t is your spread spectrum system signal, I should say. All right, signal. So this is a spread spectrum signal. So in a nutshell, I can tell you that each bit of your data which is having duration TB is multiplied with a code sequence of having length N and period TC, and TC is very small, and I should say TC into N is TB. N times TC is your TB. TB is your bit duration. All right. So you are just multiplying. This process is fundamentally, we call it as the spread spectrum technique. So normally, so I will give you some time for questions. And before that, one more point I have to mention, that normally here some of the students may get some questions regarding how the bandwidth will spread here. Yes, the bandwidth will spread if you multiply with the code. See here, in the time domain, see, you might have studied this in the time domain. If you have a rectangular signal in the time domain, what is the frequency response of this? You take Fourier transform of a rectangular signal, what you will get? You will get a single function, single pulse in the frequency domain. So if I have a rectangular pulse of duration capital T, if I take the Fourier transform of that in the frequency domain, if I plot the spectrum of the signal, the main lobe of that single function will be going up to say 1 by t. You neglect about the remaining side lobes. You consider only the main lobe. So what is this particular point? First 0.1 by t. So if t is the pulse duration here, 1 by t is the maximum frequency component there. All right. So I can say if 1 millisecond is the time duration of my rectangular pulse, then 1 by 1 millisecond, 1 by t is 1 kilohertz. 1 kilohertz is the bandwidth of this particular bandwidth consumed. The maximum bandwidth consumed is 1 kilohertz, 1 by t. If you spread that, what is the time period of the spreaded signal? Time period of spreaded signal is Tc. right? TC is very small. TC is very small. This is TB, this is TC. Second figure shows TC, this is TC, 1 chip duration. So what will be the bandwidth? So coming from 1 millisecond to 1 microsecond here, if I reduce the time period of the signal, what happens that it will spread. 1 by 1 microsecond will be 1 megahertz. So what will be the bandwidth? Bandwidth become 1 megahertz. All right. So this is the fundamental concept. If the pulse width of the signal reduces in the frequency domain, the spectrum will spread basically. So what will be the bandwidth of this particular thing? The second signal, which is having 1 microsecond duration, it will be 1 megahertz. All right. So basically, compared to the upper one, the lower one is having a higher bandwidth. So I can say spreaded signal is having a higher bandwidth. Why? Because the spreaded signal period is actually TC. TC is nothing but the chip duration of your code. All right. So this is the fundamental concept of a spread spectrum system. Okay. So this is a fundamental concept. Now, if there are any questions, then probably we can take that.
What are the applications of spread spectrum?
Okay. See, one of the fundamental applications, again, we have to mention some more parameters to well understand the applications of a spread spectrum system that we will come towards the end only. But to be very simple, I can say that, what basically, we started this topic by saying that, we will compromise two things. One, bandwidth, and the other is power, to get security, right? So secure communication system is one fundamental application of this spread spectrum communication system. See, for example, if you are using some military applications and all, where we will be, we will use this spread spectrum system where bandwidth is not a concern, but security of the system is concerned. So what are the applications where we are having security as our design objective? There we can use a spread spectrum system. That is one thing. And we have few more applications for this spread spectrum system. And you can see this particular method using in a lot of applications in real time, real world. But for that, you need to understand some more parameters that we have to discuss towards the end. So after discussing those parameters, I will list out the remaining applications. The first one, I can say the major one from this particular fundamental idea that you have received, it is nothing but a secure communication system. For example, some military application where you need to send your data securely to the receiver. And the remaining set we will address towards the end. Why? Because you need some more parameters to be given. All right.
What is the main advantage of spread spectrum communication?
Yeah, obviously, that's what I have mentioned. No, the main advantage of this spread spectrum system is just the security that we have, that we are getting from this spread spectrum system. And in addition to that, we are consuming. If bandwidth is not at all a problem, we are consuming a lot of bandwidth, right? So we are spreading it off. Obviously, bandwidth is a very from a service provider point of view, bandwidth is obviously a very important point of concern. But overall, looking from bandwidth perspective, I am getting a better bandwidth. Right, I am getting a better bandwidth for the transmission of my data. That is well and good. Obviously, that is an advantage. But again, from a service provider point of view, that is not an advantage. Why? Because we will try to reduce the bandwidth as maximum as possible. But I should say, from this knowledge, so far what we have discussed, the most important advantage is nothing but we can have a very secure transmission of digital data. Why? Because nobody can send a jamming signal to my data. It will be very clear if I explain the next slide. Nobody can send a jamming signal to my signal. But even though we send a jamming signal to my signal, nothing will happen at the receiver side. If I despread, effect of that will become nullified. That we will discuss in the upcoming slides. So secure communication is one of the most important advantage of this particular thing. Yeah. Any other questions?
The question is, in the example of spectrum, you mentioned you used the code, the polar form +1 and -1. And you said we use the same code in the decoder. Is the code for the decoder same of encoder for every code?
Yes, whatever code you are using at the transmitter, same code you have to use at the receiver side for despreading. You cannot use another code. That is advantage. Towards in the next module we will be studying CDMA systems where one code is assigned for a user. If the receiver is having that particular code, then you will be able to decode the data, retrieve or despread the data. Otherwise, it's not possible. So it is mandatory that whatever code you are using at the transmitter, the same thing we have to use at the receiver. That is mandatory.
Next question: is the type of code used has any significance?
Yes, obviously the type of code. In the next session we will discuss the different types of code. The types of code used will have will be significantly affecting the performance of the system. Okay, so the type of code we normally go for something called M sequence, maximal length sequences, gold codes, Walsh-Hadamard sequences, a lot of codes that we will be using, and depending upon the autocorrelation and cross correlation properties of these codes. So type of codes actually it matters. Different codes are having different autocorrelation and cross correlation properties, so we will use our code with better autocorrelation cross correlation properties that we will discuss in upcoming session. Will be on the different types of codes. In our topic, in our syllabus, we will be discussing only two codes. One is maximum M sequence, maximal length sequence, and the second one is gold sequence. These two we will be discussing in our syllabus, but we have some more good codes like Walsh-Hadamard sequence, and a lot of our other codes are available which is having better correlation properties. So based on the correlation properties of the code, we will select the code. So it matters actually. Yes.
Thank you, sir. We can proceed with the lecture.
Okay, thank you. Any more questions, you feel free to contact through any other medium, no problem. Okay, so now coming to a frequency domain approach. So I hope my PPT is visible, right? Okay, fine, all right. So now let us discuss the frequency domain approach. What we have previously mentioned is a time domain approach, where we will multiply your signal in the time domain with your code, which is shown in the time domain. Now, what happens in the frequency domain? This is your baseband signal. Baseband signal means your low frequency signal, or I should say your messy signal, a signal with significant low frequency components. So this baseband signal, after multiplication with the code, we now know very well that it will spread the spectrum. The spectrum is spreaded something like this. All right, now come to the bottom figure. See here, this one is the desired signal. You can see the desired signal. Desired signal is your spread spectrum signal. Okay, this is what you are transmitting. To that, an unintended user is adding some interfering signal, so-called a jamming signal. Okay, so to that desired signal, an unintended user is adding an interfering signal or a jamming signal. Now what happens at the receiver after a despreading process? What I am doing is the actual desired spectrum signal, if multiplied with the same code, right? If multiplied with the same code, you will get back your actual data. So, right? You can see here. I will show in the previous diagram, right? What will happen? This is spreading, right? What I have mentioned here is spreading. What will happen at the despreading part? Once if you despread, what will happen? So I will show here what will happen at the despread. See here. This is your spread spectrum signal, right? And what you are doing at the receiver side? At the receiver side, you are multiplying this product signal with the same code. With the same code. Your code is here. This is your code. You can see the code. This is your code. This is your code signal. So at the receiver side, you are multiplying. At the despreading part, you are multiplying this signal with the same code. So see what happens. -1 multiplied with -1. It is 1. Here also -1 multiplied with -1. 1. 1 multiplied with 1, 1. So whatever it is, you are multiplying the same sequence, right? This one with this one, right? You can see the third figure and for the middle one and the bottom one. Multiplication of these two will give you 1 always. So you are getting back your data. This is despreading. You are getting back your data. All right. Similarly, what happens the other part? Here, -1 multiplied with 1, -1. Similarly, -1 multiplied with 1, again -1. Whatever multiplication you do, this part, +1 multiplied with the bottom -1, you will get -1. So this multiplication, the right part, the second bit, this multiplication will give you -1, which is your actual data. So that means if you multiply your spread spectrum signal with the same spreading code, you will get back your data signal. This is the fundamental, the concept that this is what we are utilizing. This idea is what we are utilizing at the receiver part while despreading. All right. Now see here what happens if I despread. You can very well see here that after despreading, you will get back your desired signal. This is your actual data, which is your narrowband signal, the previous one, the what you have transmitted. And what happens to the interference signal? Interference signal will get spread out. Why? Because interference signal, the jammer is a narrowband signal. The jammer has no idea that I am having a wider spectrum. So jammer will send that narrow band jamming signal. So at the receiver side, once if I do despreading process, I am multiplying my spread spectrum signal as well as this jamming signal with the same code. So what happens if I multiply jamming signal with the code? Jamming signal will spread. This is shown here. So interfering signal will spread its spectrum. So the noise component coming from this interfering signal or the jamming signal will be very less. So I can simply use a filter, this with a narrowband filter to get the data back. Right? Nothing will happen. And in that narrowband part, since the jamming signal is spreaded, the noise power from this jamming signal will be very small. This is shown here in the shaded portion. All right. So that is advantage. Jamming signal can do nothing with my actual transmission. Jamming signal can no way affect my actual transmission. This is the main advantage of a spread spectrum communication system. All right. So this is the whole idea. Now, sorry. Now let me introduce a parameter called processing gain. Okay, so this is one parameter I will introduce, and later in probably I am not sure whether we will be able to derive that today, but probably in the next session we will be able to derive an expression for this processing gain. Then you will understand the fundamental concept of what a processing gain is. All right. So for the time being, I will give you the definition and fundamental idea of what is processing gain. Okay, processing gain is the gain in SNR, right? It is whatever gain you are obtaining in the whatever SNR gain you are obtaining by using this spectrum modulation technique, that is actually represented by processing gain. Also, or I should say, processing gain indicates SNR gain in SNR. Okay, and what is SNR gain? You observe the receiver part, come to the receiver part. You will get some signal at the output of receiver, and you will be giving something to the input of receiver. You check the SNR at the input of receiver. You check the SNR at the output of receiver. Take the ratio SNR at the output divided by SNR at the input. You always want that to be maximum, right? Always we want SNR to be maximum, right? Always we want SNR at the output to be maximum as possible. All right. So this ratio of SNR at the output of the receiver system divided by SNR at the input, that ratio is called the processing gain. Okay. Or I can give one more definition for this. It is actually, in very simple terms, it is actually the spreaded bandwidth divided by that signal bandwidth. Or in the previous figure, this is, you can see the spreaded bandwidth here, right? Spreaded bandwidth, which is very, very large. This is a spreaded bandwidth. All right, you can see, and that divided by that signal bandwidth, which is a very narrow bandwidth. So that ratio, spreaded bandwidth divided by signal bandwidth, is called a processing gain. All right, and I should say, this processing gain is an approximate measure of the interference rejection capacity of my spread spectrum system. Okay, so if I know the processing gain, I can say some observations about the interference rejection capacity of the system. All right, so this is an approximate measure of the interference rejection capacity, or I should say, to be very specific, this is the gain in SNR obtained by using a spread spectrum modulation technique. All right, and no, it's very simple, right? What is processing gain? Spreaded bandwidth divided by actual signal bandwidth, or that is in the frequency domain. That is in the frequency domain. Or you come to the previous one, what it will be? This is actually TB divided by TC, right? That is a spreading factor, right? spreading factor in the time domain will be TB, which is now reduced to TC. All right. So what is that factor? N. So I can say here N as the processing gain, or I should say TB by TC. You can see in the screen TB, the bit duration, the time period of the bit of your data signal divided by time duration of your code signal. That ratio is the processing gain of the system. All right. So we have defined processing gain in two aspects. One is a frequency domain. It is, I can say it is a spreaded bandwidth divided by actual signal bandwidth. And in the time domain, I can say it is TB, bit duration of your data, actual data divided by bit duration of your chip, TB by TC. Or I should say N is the processing gain. All right. I hope you can see this PG processing gain is equal to TB by TC, right? Or I can write this as 1 by TC divided by 1 by TB. I can rearrange it. Simply I am rearranging. All right. Then what is 1 by TC? 1 by TC is, it is a chip rate, number of chips per second. All right, it is a number of chips per second. Say for example, your TC is, say for example, I should say, suppose, assume, you visualize, assume your TC is 0.5 seconds. So 0.5 seconds for the time being, a random example, not exactly, not having any practical relevance, but still you take 0.5 seconds. 1 by 0.5 second will be 2. That means in 1 second you have 2 chips. All right, in 1 second you have 2 chips. So if your TC is 0.5 seconds, 1 by TC is 1 by 0.5. 1 by 0.5 is 2. That means you have 2 chips per second. I call it as a chip rate. So chip rate is actually the number of chips that we are having per second. Similarly, 1 by TB will be number of bits per second. That is the bit rate. So another definition for processing gain is chip rate divided by bit rate. I hope it is very clear. All right. So RC by RB. This is the definition for processing gain. Now quickly we will move to the different types of a spread spectrum. Normally we deal with 2 different types of spread spectrum systems. All right. So we have 2 different types. The first one is direct sequence spread spectrum, or DSSS, direct sequence spread spectrum. And the second one is frequency hopping spread spectrum, FHSS, frequency hopping spread spectrum. All right. Now, so let us first discuss the first one, which is a direct sequence spread spectrum. All right. Nothing to worry. What we have discussed so far is actually the fundamental principle of a direct sequence spread spectrum. What we have discussed so far? So far what we have discussed is nothing but multiplication or product of your message signal with your carrier. You are taking the product of message and data and carrier. I mean carrier in the sense code. I'm sorry, code. It's not carrier, it's a code. So you are taking the product of data and code. Right. This is the same the concept behind the direct sequence spread spectrum system. Okay. This is DSSS only. Frequency hop is having some difference. We will discuss in next session probably. Okay. Now we are just multiplying data, which is a narrowband signal, with a code. Right. This is baseband. This is the baseband. All our discussions, this product, everything is in the baseband. But now come to, see for example, a satellite communication scenario where you will be using a band pass channel, a high frequency channel. All right. In a high frequency channel, can you do this baseband multiplication? It's not possible. You have to always go for a high frequency carrier. You might have discussed, you might have studied our digital band pass modulation techniques. About our digital band pass modulation techniques, some of them are Bpsk, binary phase shift keying, QPSK, quadrature phase shift keying, 8PSK, or whatever advanced schemes. So coming to a band pass channel, for example, a satellite communication channel, or any channel where mobile communication channel, whatever, any channel where we are using a high frequency, where we need a high frequency carrier. Right. So previously, in the previous slides, what we have discussed is simply the baseband transmission. Now, if you are discussing, if you need to analyze over a band pass channel or a high frequency channel, then obviously you have to incorporate what coherent PSK modulation schemes, binary phase shift key modulation schemes, into both transmitter as well as receiver. Right. And combine these two, you will get DSSS, direct sequence spread spectrum. Okay, I will reiterate. In a direct sequence spread spectrum, I'm having spreading product of message, data, and code plus a binary phase shift keying, some bandpass modulation technique. Normally binary phase shift keying or QPSK. So this spreading plus a high bandpass modulation, technique. Combination of these two is nothing but, you can see this in the figure. So I have two stages in a direct sequence spread spectrum system. One is a product modulator and the second is a BPSK modulator or binary phase shift keying modulator. You can see here. Okay, so one more thing is coming into picture in the DSSS thing, which is nothing but, why? Because this is a bandpass channel. Previously what we have discussed is a baseband channel. Now we are coming to a bandpass channel where we need a carrier. We need a high frequency carrier for transmission. No other options. All right. So here, so B of t data sequence multiplied with the code, then you give it to, you can see you give it to a binary PSK modulator, and output of this is x of t. You can observe in figure. You can look at the screen. You can see x of t. What is x of t here? Think what is x of t here? X of t is BPSK modulated version of your spreaded signal. Right? It is BPSK modulated spreaded data signal. That is direct sequence spread spectrum. Right? That is x of t. All right. Now coming to the receiver, you will use the same PN code because there is no other option. You have to use the same code, otherwise you will never get back your message. So you have to use the same carrier. You have to use the same PN sequence or code at the receiver to multiply, then give it to a detector, coherent BPSK detector, where you need the same carrier. You might have studied, BPSK and all you might have studied. What we are doing in BPSK? For general information, this is what we are doing in BPSK. Quickly I will tell you. Suppose I have a data 0 and 1. How I will BPSK modulate that? 0 will be represented as in its polar form say -1, and 1 will be represented in its polar form say 1, say +1 and -1. Now corresponding to 0, its polar form is -1. What I am transmitting is -a cos 2 pi fct. I am transmitting a -a cos 2 pi fct, a cosine high frequency carrier. Corresponding to 1, what I am transmitting is a cos 2 pi fct. All right. So in BPSK, what you are transmitting? In BPSK, either you are transmitting a cos 2 pi fct corresponding to 1, or -a cos 2 pi fct corresponding to 0 or polar -1. All right, which is very well shown here in this particular diagram. Okay. And what is required at the receiver? At the receiver, what is having at the BPSK receiver? At the BPSK receiver, you will multiply with the same carrier. Your carrier is a cos 2 pi fct. Your carrier is, you have only one carrier, a cos 2 pi fct. That a cos 2 pi fct, you will transmit as a cos 2 pi fct if your data is 1, or you will transmit as -a cos 2 pi fct if your data is 0. All right. Now at the receiver side, what you are doing is you will multiply with the same carrier, then integrate, pass it through low pass filter, whatever. Okay, we call it as a correlator receiver. Okay, so you will use this correlator receiver for detecting this BPSK signal back. This is what it is shown here, a coherent detector. So there you need a local carrier. All right. So this is a direct sequence spread spectrum modulation technique. All right. So you can see the phase change, either A or -A. All right. So I will quickly highlight it here. You can see corresponding to -1, you are transmitting -AC cos 2 pi fct. All right. And corresponding to 1, you are transmitting +AC cos 2 pi fct. Again -1, you are transmitting -AC. This is normal BPSK, right? So this is a direct sequence spread spectrum signal. Okay. Now let us if time permits, we will at least do the initial portion of this. We will move to a mathematical model for analysis of this spread spectrum system. Okay, so direct sequence per spectrum, I hope the block diagram is clear. In block diagram, you have two parts. One is a product modulator, and the second one is nothing but a coherent BPSK modulator. Okay, these two are there in DSS system. Now let us have a mathematical analysis of this. Anyway, I may not be able to complete the entire mathematical model of this, but analysis of this, but I will give you a whole idea. What we are trying to do is, we will observe, we will use some mathematical expressions to represent this direct sequence per spectrum system. From there, gradually we will analyze what is the jamming signal, what is the nature of jamming signal, is it random, if so what is the mean, what is the variance, everything we will understand. And finally we will derive an expression for processing gain. First, processing gain, I mean, SNR the output, SNR the input, all these things we will find, and we will derive an expression for processing gain. And the last portion will be derivation of its probability of error, right? Anyway, noise is there, some error chance will be there because of the noise. So we have to derive an expression for the probability of error. These things we will obviously discuss in the next session, but at least we can start quickly in this initial, at least this model we can complete today. All right, so here in this particular thing, you can see the block diagram, which is slightly rearranged. So previously, initial portion was spreading, followed by product modulator, but I have interchanged that. Nothing will happen. No, anyway, if you keep one as stationary, other one will be anyway linear. So I can interchange. Nothing will happen. So I have here first I mentioned BPSK modulator, then followed by P encode. I am simply swapping that order. That's it. So B of t is your data signal, which is given to a binary PSK modulator, where you are having a carrier. Then after modulation, you are having something called S of t. S of t is actually your transmitted signal. You multiply with your code C of t, you will get X of t. What is X of t? X of t is, listen carefully, X of t is your spreaded BPSK modulated signal. X of t is spreaded BPSK modulated signal, or BPSK modulated spreaded signal. Now it is passing through a channel where I have the jamming unintended noise, which is J of t, and coming to the receiver we have Y of t, and this Y of t, first you are doing is exactly the reverse process. You are multiplying with the same carrier C of t, and the product I represent as U of t, which is, what is U of t? U of t is after despreading. After despreading, what you will get? Your BPSK signal. So what is next step? BPSK demodulator. That is coherent detected here, where you need the local carrier, and you will have the estimate of B of t. All right. So this is a fundamental direct sequence spread spectrum system. All right, where Y of t is X of t plus G of t. All right, Y of t is X of t plus G of t. Then, and what is this X of t here? X of t is S of t into C of t. Right, it is very clear here, S of t into C of t. That is written here, S of t into C of t plus your jamming noise J of t. Right, so I can say, what is U? U is actually Y into C, received one multiplied with the same code. So U of t is Y of t into C of t. So Y of t can be written in terms of S of t into C of t. No, it's self-explanatory. From the figure itself, you can understand and write S of t into C of t plus G of t, the whole into code, the same code of the receiver. All right, and bringing this back, we have S of t is equal to, this is S of t into, or U of t is equal to S of t into C square t plus G of t into C of t. Okay, so after this coming to this particular, we will finish. We will stop for today. But before that, one point I have to mention here: what the C square t? What is C square? C square is actually the square of your code sequence. Square of your code sequence. What is your code sequence? You can see here. See here your code sequence. This is your code sequence. What you take the square of code sequence minus 1 square 1 in the polar form. You take square. Polar form, you take square, C square, you will get 1, always 1. So C square of t will be 1. C square of t is always 1. I hope it is very clear. Polar form, you take square of that, it will be always 1. All right. So that is the reason why I have mentioned here C square t is equal to 1. That is the reason I have mentioned here the C square. You can see here C square t is equal to 1. So your U of t becomes S of t plus J of t into C of t. And what is S of t? What is S of t? S of t is actually your, it is after despreading, right? You have already multiplied with your code. So it is despreaded. So after despreading, what you will get? You will get your Bpsk signal. So it is Bpsk signal plus spreaded version of your interference. You have some jamming signal, right? So jamming signal itself will spread during our actual despreading. During our actual despreading, the jamming signal will spread. All right. So I am getting U of t. U of t here. This U of t is having two components. The first component is a binary Psk signal, and the second component is a spreaded interference. The interference will spread. Okay. So I mean, I think we can take, if any questions are there, we can take a couple of questions. Otherwise, no. I mean, shall we proceed or?
Sir, we have a few questions.
Okay. Then we will take some questions. Yeah. All right.
As we are stretching the signal, even though we use the same code at transmitter and receiver, won't there be an error due to this?
There will not be any error because of this. Why? Because, see, observe this figure, this particular figure. I will show here. See, I mean, I hope it is visible. Some kind of error will be there if channel is introducing some noise. Obviously, that we have to take care. If channel is introducing some error will be there. That towards the, in the next session we will derive an expression for the probability of error. That is one part. If channel is introducing some noise, error definitely will be there. Otherwise, if channel is not introducing any kind of noise, then see here. This is the code. This is the actual spreaded sequence. You are at the despreading part. You are multiplying your product signal with the same code. Right? You multiply these two. -1 multiplied by -1. You will get 1. -1 multiplied by -1. You will again get 1. You multiply these two. You are multiplying. Despreading means multiplying the same code, right? You multiply these two, the middle one and the bottom one. You will get the upper one, right? So provided there is no channel noise, there will not be any error. If you use the same code, you will get the message back. Otherwise, if there is some channel noise, obviously some error will be there. Channel definitely will be introducing some noise. Then we have to understand the channel. We have to observe the channel. We have to study the channel, and we will model our system accordingly to reduce the channel, to reduce the error. I hope I have answered.
Yes, sir. Thank you. Is Wi-Fi spread spectrum?
No, Wi-Fi is not purely spread spectrum system. In Wi-Fi, we are using some kind of modulation technique called orthogonal frequency modulation technique, OFDM. So this is not actually a pure form of spread spectrum signal spectrum. In the 6th module we will be discussing something about OFDM. So it's actually kind of an OFDM modulation involved in Wi-Fi. It's not a pure spread spectrum system in its raw form.
Thank you, sir. What is the role of pseudo noise sequence in spread spectrum?
Pseudo noise sequence in spread spectrum. Pseudo noise sequence is actually a signal with lesser time duration, TC. Right. So I am multiplying my actual data signal with a signal having lesser time duration. Here it is visible. Okay. So what happens is that the product signal you are getting, or the multiplied signal, what you so-called the spread spectrum signal you are getting is now having a time period which is very small, TC. So this is how spreading is happening. So pseudo noise sequences are having some properties where correlation is obviously one thing. I will explain it very clear later while studying different types of noise, pseudo random sequences. But in addition to that, the correlation properties, it is having a time period which is very less, which is almost very small, TC. So that lesser time period will result in which results in the broadening of the overall spectrum. So spreading is actually because of this pseudo noise sequence, which is having a very less TC. Hope I have answered. Some more properties are there for the pseudo noise sequences that we will discuss later. We have to study that. We will discuss in the upcoming sessions. Yeah.
Okay, sir. Thank you. The next question is, how do you decide the number of chips and how does it affect the SS signal?
Now, so-called we have designed something called we have defined something called a processing gain, right? So what is processing gain? Processing gain is actually the gain of SNR. It is actually the SNR gain, right? So we have already mentioned here. Processing gain is, now I will come to that slide. So yeah, processing gain is actually TB by TC. And what is TB by TC? TB is the bit duration, TC is the chip duration. What is the ratio? N is the number of chips. All right. So the number of chips is actually related to that spreading factor or that spreading range. All right. So depending upon whatever applications what we are having, we can select our spreading factor. Right, whatever is designed, whatever is required for us, whatever SNR gain is required for us, depending upon that, we can have our, we can design our N basically. All right, and one more thing that we will be discussing in the next session only. There are some methods that we normally follow for the generation of these code sequences. All right, so I should say from this point of view, whatever information I have shared today, I can say that processing gain or the gain of SNR of the system is somehow related to the number of chips that we are using. All right, so that depends upon the system that we are designing, our requirements basically. So I hope I have answered that question.
Yes, thank you, sir.
Yeah.
Consider I am a spy. How can I retrieve the data without the code?
How can you retrieve the data without the code? If you don't have the code, it is very difficult. We are not dealing with any security hacking type of methods, but still, from the basic fundamental concept of a spread spectrum, if you don't have the code, you cannot retrieve the data back. If you don't have the code, you cannot retrieve the data. You can have any kind of. So that is the reason why these hackers, or I should say the unintended users, are doing some trial and error methods, some brute force methods. They will try all possible code sequences, and somewhere they will end up with the actual code sequence. Otherwise, if you don't have any idea about the code sequence, it is absolutely extremely difficult. It's not at all possible to get the exact data back from a jammer point of view. So from a but jammer has many methods, right? Jammer obviously will be trying many methods. They will be trying some random methods. They will try to predict our code signal. Some kind of. We are not concerned about the methods done by the jammer. But from our point of view, if that person is not having, if that person is not getting the actual code, no way he is not. It's not possible to get your signal back from your spectrum signal. You need the actual code. Hope I have answered.
Yes, sir. Thank you, sir, for answering all the questions. Sir, can you please say some important questions in spectrum communication exam point of view?
From exam point of view, normally we might have. In the previous question papers, you might have seen one important question is the block diagram of and the explanation of a direct sequence spread spectrum. So it's something like with the block diagram, you explain a direct sequence spread spectrum system. So we have to explain this particular block diagram and followed by its explanation. That is one thing. And the second thing, second one that normally asked is the definition of processing gain. So again, processing gain is yet to complete. We have a derivation for this processing gain. So sometimes they may ask the derivation of processing gain. So you have to derive all these processing gain and all. Today we have mentioned only the concept, fundamental idea of processing gain, but obviously in the next session we will derive what is processing gain, that is required, and the probability of error. So again, that we will discuss in the next session only. So from today's point of view, the fundamental concept, you may have some short questions like the concept of spread spectrum, then direct sequence spread spectrum, which normally will be an essay question for you, then processing gain will be a very important aspect. Some problems may come from processing gain, right? You may given some of the parameters and they will ask what is a processing gain. Some problems will come. So these are the important topics from this area that we have discussed today.
Okay, sir. Thank you. Sir, anything more to add?
Yeah, so probably I hope it's almost very clear in this particular session. So nothing more to add. We will have more discussion in the upcoming sessions where we will have more mathematical analysis of this. Whatever we have discussed here, we will have more mathematical analysis in the upcoming sessions. Yeah, that's all.
Okay, thank you, sir. Thank you for spending your valuable time and for your wonderful session covering the topic spread spectrum communication.
Thank you so much. Thank you so much.
Explained the concept and it is really informative. Hope our students will surely be benefited by this session. The students can access the whole session in SAP YouTube channel. Once again, thank you, sir, and thanks to all the participants.
Okay, thank you so much. Thanks for this opportunity. Thank you.